Chapter 15 and 16, slides 1 through 8. So far, we have learned a lot of techniques in the Organic Chemistry 1 laboratory. But most of the techniques that we've been looking at have been dealing with purification methods, which is an extremely important thing to do. If I want to know what a molecule is that I have in my possession, I might have done a reaction and made a new molecule, or maybe I found a molecule in nature that I want to study. Purifying it so that you have only that molecule to study is really important in order to focus your energies in figuring out what that molecule is. So if you use an instrument to probe that molecule, say melting points. Melting points are pretty much the only type of identification type instrument you have used so far to validate or support the fact that you have one molecule versus another. And if, as you guys have learned, if your molecule is not pure, if you have impurities or byproducts, the melting point is not going to be precise, right? You will see melting point depressions, and thus that mucks up your ability to, say for certain whether or not you have one molecule or another. So melting points to this point are really the only instruments you have used for identification. Everything else has been largely purposed for purification, which, as I mentioned, is important in order to use for identification purposes. We've used TLC and column chromatography, and we've used the properties of the molecules, namely polarity in those cases, to understand how and expect which ones are going to come off the column first or, hang behind based on polarity. You can use distillation, and this uses the properties of boiling points to separate molecules. You can use phase. Do you have a liquid and a solid, which you can filter? Solubility becomes an issue as you guys move to extraction chemistry later on. Does the molecule dissolve in a water layer, or does it dissolve in an organic type of solvent? So a lot of these techniques are used to purify your compound, right? Once purified, then you can do identification techniques on the molecule. So we're going to be moving towards how to figure out what you have in your flask, right? And there's lots of different scientists that need to know what is that stuff, right? For instance, you could have a forensic scientist looking at a substance found at the crime scene, right? And what is that substance? Is it a drug? What type of drug is it? Or studying, drug trade and wondering what's the new stuff out there? Is it cut with something? Perhaps someone dies and they pump their stomach and they want to know what's in the contents of that stomach. Perhaps there was an arson and there was a fire and they want to know what the accelerant was that started the fire. So what is that stuff is very important to a forensic scientist. Analytical chemists use instrumentation all the time to figure out what that stuff is, right? Smoke coming out of a stack. Is it a pollutant? How much is it? That is the bad pollutant versus the maybe more benign water condensation that we see. The atmosphere, studying the components of the gaseous molecules in our atmosphere. Do we have more of one substance over another? What is the composition? Perhaps there's a plant. Maybe the plant has been used for years in herbal medicines, and we want to know what compound in the plant is actually doing all of the biological work. So we want to purify all the substances from one another and study the components of that plant. Lake water, right? What's the pollutant in the lake water? What is the composition of other molecules in that water? Organic chemists, what you guys are going to be doing in lab, is simply, I'm going to make a new molecule, maybe for the purpose of a pharmaceutical, maybe for a material, maybe a design that you're trying for the first time, and you're not sure if you've made the compound you wanted. How do you know? It's a new compound. It doesn't have a melting point reported in the literature. It's never been made before. So how do you know you made what you made? Perhaps you want to test the purity of your starting materials. Perhaps you want to identify a side product that occurred in 30%. It's big enough that you want to investigate it. How do we know that what is in my flask, or what is in the air, or what is in the water, or what was taken from a crime scene? How do we know that stuff is the molecule we presume it to be? Well, to do that, we use instrumentation. And unfortunately, there is not one magic instrument that just you insert the molecule and out pops the answer, right? We have to do a lot of puzzles and investigating in order to figure out what that molecule is. Now, if the molecule is a known compound, oftentimes its data on certain instruments is logged in a library, and you can actually run the substance against the library of compounds that are known. So for instance, a forensic chemist may only use like a mass spec down here. Here's the mass spec. And this is the mass spec at RIT. They might run just a mass spec on a solid substance found. If they're thinking it's a drug and they want to know what drug it is, they can run the substance through a mass spec. And there's probably a library at the headquarters of all of the illicit drugs they have on file, and they can run it, and it's like a fingerprint, and they can get a hit. The problem comes when you don't know what the molecule is. Like if this is an unknown molecule, then it's not going to be in the library that's been programmed. So we have to figure it out. We've got to discover what that substance is. And if we're working with unknown compounds, and especially when we do figure it out and want to publish our results, we definitely need 5 different types of instruments to corroborate and support our claim to, the answer to the puzzle. If I made a new compound and I was trying to publish my paper, I can't just say, oh, I took a mass spec and this is what I think it is. It would be rejected. I need to show evidence that is all corroborated by multiple instruments pointing to the same thing. And each instrument tells me a little bit more to the puzzle. And what I want you to notice is that and before we start talking about these individual instrumentations, we're going to be focusing on spectroscopy and spectrometry. There are other instruments and methods out there to help with figuring out what the molecule is. There are chemical tests. This is actually where you do chemistry to figure out whether or not you have an aldehyde or an alcohol. Elemental analysis. Very expensive. Few departments have an elemental analysis instrument, and they require a very pure sample. They're a little expensive to run, so we don't go to them all the time, but oftentimes they're required as one of the instruments for publication. Spectroscopy and spectrometry are what most departments will have. We have plenty of instrument methods that fall under this spectroscopy and spectrometry category. X-ray diffraction is also something that can be used, but obviously your stuff has to be a solid. You have to grow a crystal, and that crystal has to be grown pristinely, perfectly, and you have to give it to an X-ray crystallographer who runs the X-ray diffraction on that molecule. And that is expensive, requires an expert X-ray crystallographer to run it for you. This is not one of those things that you just go down and do yourself. And very few places have them. So, you kind of have to go to one of the facilities that has, a paid X-ray crystallographer on site and have them run it for you. And you have to hope that you grew your crystal to their satisfaction. And lastly, optical rotation. We do have a polarimeter here at RIT, but that optical rotation is one of the pieces of evidence, but it's not going to really tell us what molecule we have. Okay, so we're going to focus on spectroscopy and spectrometry. And if you'll notice, it's called a mass spectrometer. And for the 2 instruments on the right, I have a picture of the infrared spectroscopy at RIT. This is in the lab right next to where you guys are working. And we also have an NMR, which is also another means of spectroscopy. So what's the difference between a spectrometer and spectroscopy? Spectroscopy is when an instrument hits the molecule with some type of energy, right? And it could be radio frequency, could be infrared, it could be UV. And we look at the behavior of the molecule when it gets hit with that energy. So spectroscopy is using energy and looking at how different molecules absorb that energy. Spectrometry, down here at the bottom, doesn't hit it with energy. It doesn't use a type of energy and then we look at the behavior. It works by a completely different modality. So we group the first four I have here as spectroscopy because UV vis uses the energy of UV light and visible light, and so that energy, and we hit the molecule with UV and visible light, and we look at the behavior of the molecule. And what it tells us is something about the conjugated double bonds in the system. So if you don't have conjugated double bonds, meaning pi bonds that can resonate with other pi bonds nearby, if you don't have that, there's no reason to run a UV vis. Infrared spectroscopy, we hit the molecule with infrared energy, and what comes out, we understand how to read what functional groups are present. Doesn't tell us how many functional groups or how things are connected. It just tells us you have an alcohol or alcohols. You have a carbonyl. You have a double bond, right? So it tells us what's present. Nuclear magnetic resonance spectroscopy helps us identify carbon-hydrogen framework. This is the big one that tells us a lot more about connectivity. So you can see how each spectroscopy instrument tells us a little bit more of the pieces of the puzzle. And then mass spectrometry, this one helps us determine molecular mass. So although it uses a different modality, it does tell us information, but it's a spectrometer. So I'm going to go through each one of these, and we're going to do an overview of each instrument, how it operates, and what the spectra look like for the given instrumentation. We're going to start with mass spectrometry. Okay, as I mentioned, mass spectrometry is different from the rest. Why? We're not hitting the molecule with a type of energy. What's happening is that you're taking your sample, and unlike the others, so I'll go back here for a second. So the spectroscopy methods, when you have a sample that you're studying and you've purified it, and you go to the UV vis instrument or the infrared instrument or the NMR instrument, you're just hitting it with some energy and observing the behavior. If you wanted to take your molecule back after you run the instrument, you totally can. Nothing has happened to you. It's like when you go to the doctor and you get an x-ray or you go for a type of ultrasound scan, you're intact afterwards, right? They're just kind of using energy and looking around and checking things out. Spectrometry, however, your molecule typically is unrecoverable because what's happening is that you're fragmenting the molecule. So you have to have a sample of your compound, but don't expect to get it back. You're actually blowing it up to smithereens. You're taking your sample and you're injecting it into the mass spec. And what happens is that there's an electron beam here. That's where all the magic is happening. Okay, and the electron beam is hitting your molecule. So let's just say we had an ethane type molecule down here. Okay, the beam of electrons is hitting that molecule and ejecting an electron. So think about the bond between these two carbons. You're like bombarding it with electrons. You're hitting it. You're making it explode in a sense. You're fragmenting it. So one of these electrons literally flies out, right? So that's shown right here. The electron flies out. The other one is left behind as a radical. And so you end up with a radical cation because the system lost an electron, so it's positively charged, and you have this one remaining unpaired electron behind. And because it's a charged species, the instrument is able to detect it. And so neutral molecules, neutral fragments, and negative ions can be pulled through this analyzer tube. and the positively charged ions are deflected and read by the recorder. Okay, and so all we're going to see are radical cations. But remember, electrons don't really weigh much, do they? So ejecting an electron from the system allows us to have a charged species, but it didn't affect the mass of the molecule. Thus, we are going to be able to understand mass fragments. Now, here's the cool part. If I have a molecule, let's say I have this molecule right here, 1, 2, 3, 4, 5. This is pentane, right? Okay, I got pentane. Now, what's the molecular mass of pentane? Pentane is C5H, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So if I were to do the molecular weight, molecular mass of pentane, I would say 5 times 12 is 60, right? 5 times the weight of carbon is 60. So 5 times 12 is, that's for carbon, 60, plus 1 times 12, because there's 12 hydrogens, right? These are the hydrogens. So if I take 60 plus 12, I get 72, right? So 72 grams per mole is the molecular weight for pentane. So if I inject pentane into a mass spec, what's going to happen is this. The electron beam is going to bombard the molecule and just completely decimate it. It's literally like you threw a bomb at pentane. Now here's what's really cool about mass spec. Imagine you walked into the kitchen, took a plate off of, out of the cabinet, and you smashed it on the floor. That plate would shatter into pieces, right? Now, if you took another plate and you shattered it on the floor, it would probably smash into pieces, but the pieces would be different than the first time you did it, right? Well, this is what's kind of cool about mass spectrometry and molecules and how they behave in a mass spec. When you bombard the molecule with electron beam, it blows up into fragments, right? Just like our shattered plate. But if you use the same molecule every time and you hit it, it'll fragment into the same pieces every single time. So it's like there's a fragmentation pattern, right? Which is almost like its fingerprint, but it fragments the same way every single time. So it'd be like going into the kitchen, and every time you shattered a plate, the exact same fragment pieces would be seen. So it has this pattern to it. What's happening is that the molecule is getting bombarded, and it's getting, all of these bonds are getting chopped, right? So if I chopped it here, let's say A, I would get the fragmentation pattern A right up here at the top, where the methyl radical and the CH2 carbocation would be formed. And if you take the masses of these fragments, you'll start seeing them as the masses shown to the left here. If I had maybe chopped the molecule here, we'll call that B, then I would see this fragmentation pattern. You would see the ethyl on one side and the propyl on the other. And because they're charged, given the fragmentation, you see that it's the mass minus the mass 29 on the left. And so, again, you can pick a different fragmentation area. If I fragment it here, I would see this fragmentation pattern, and so on and so forth. And so the masses of each one of these things highlighted in green are the peaks that you're seeing, the fragmentation pattern. The bigger the peak, the more abundant that fragment piece is. That fragment is a bigger piece, like meaning we see it more often that is the preferred piece of the breakage. Now, what do I want you guys to get? Well, down here at the bottom is the mass to charge ratio. That's what M over Z stands for. Really, it can be read as the mass because the charge is very small, but it's what is being picked up by the instrument. So how big the peak is its relative abundance. So you can see in this chart that the mass is on the left and the relative abundance of that piece is on the right. I'm not too concerned in this class about relative abundance. That's something that you'll study the hows and the whys in another course. For instance, you guys have learned in chapter 6 and 11 that radicals prefer to be on tertiary better than secondary, better than primary. So just at a base level, if you're going to fragment this molecule, putting a radical on a secondary versus, here, if you look, this is a secondary radical versus a primary radical, is probably going to be preferred. So you can relate relative abundance of these fragments due to their preference of intermediates, radical intermediates. A more stable radical will probably be a higher abundance than a less stable radical. But let's put that aside. I just want you to know you have the ability to look at some of this and make sense of it. But what I want you to do is, first and foremost, I want you to be able to recognize a mass spec. That the x-axis is m over z, mass to charge ratio. That the y-axis is relative abundance. And what are you going to get from it? I want you to recognize the parent ion peak. So this is what I want from you. This is what a mass spec looks like. And where's the parent ion peak? The molecular ion peak is given right here. It's the one where all the molecule lost was the electron, and electrons barely weigh anything. So the peak farthest to the right is the one that should be the mass of the molecule intact. Intact minus one electron, that is, right? And we already calculated that pentane has the molecular weight of 72 grams per mole. And if you look farthest to the right, it doesn't matter with the relative abundance, that is your parent ion peak. That's your molecular ion. That tells you what the mass of the molecule is with just the loss of one electron. All the other ones that come before it are the fragmentation peaks, different varieties of the fragmentation pattern. Now, as I mentioned, you could take this pentane substance. Every time I inject it into the mass spec, I'm going to see this same fragmentation pattern with the molecular ion peak farthest to the right. So this is how we can catalog them and put them into a library once they are known compounds. Sometimes we don't know what the compound is, and we get a molecular ion peak, and we get fragmentation patterns. And often we can decide that the molecule has a given formula. We might say, oh, the mass spec is telling me I have a C4H9Br, but I don't know what the molecule is. So what I wanted to do is take a moment before going into the next piece of instrumentation and talk a little bit about what happens when we know the molecular formula, but we don't know anything else about the structure. And one of the things that can help you guys when determining unknowns is calculating the degrees of unsaturation. I've used the term saturation and unsaturation before relative to having a pi bond or a ring. But I want to formally give you the equation, which you do not have to memorize. I will give this to you on an exam should you need to use it, but you just have to know how to use it. So let's start with molecular structure. When you know the molecular structure, okay, let's take example A at the top here. I look at that structure. I have the structure in front of me, so I know I know exactly how to calculate degrees of unsaturation. Now, a degree of unsaturation means that there's either a pi bond or a ring. So every pi bond counts as a degree and every ring counts as a degree. So if I look at A, I see that there is one pi bond and no rings. So this is 1 degree of unsaturation. If I look at the example to the right, there I can see the structure. When you can see the structure, it's very easy. You don't need a formula. All you have to do is look at the structure. The structure has a ring, right? And it has a pi bond. So my degrees of unsaturation, I get 1 degree for the ring and 1 degree for the pi bond. So this has 2 degrees of unsaturation. What that means is that a ring and or a pi bond are taking hydrogens off. We don't have as many hydrogens saturating the number of carbons present, right? Do the formula. 1, 2, 3, 4, 5, 6, 7. This is a C7 molecule. 1, 2, 3, 4, 5, 6, 7. C7 molecule, if I didn't have any rings or double bonds, C7 would be 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, how many hydrogens would C7 have? C7, H, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. C7 in its saturated state would have 16 hydrogens. That's total saturation with hydrogen. Because I added a double bond, right? Let's count the hydrogens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Well, if 16 hydrogens is saturated for 7 carbons, then when I have 7 carbons but 14 hydrogens, I am unsaturated by 1 degree. That's what the meaning is, okay? And you can try it. Try that with molecular formula for the molecule to the right. This is also C7, right? But I have 2 degrees. So how many hydrogens are there going to be? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Notice how the number of hydrogens keeps dropping by 2. So number of degrees is very easy to read when all you have is the structure in front of you. But what if you were running a mass spec? And the mass spec points to the fact that you have a C5H12 molecule. Okay, so now we're down here. C5H12. I want to know how many degrees of unsaturation I might be playing with here. It's not going to tell me if I have a ring or a pi bond, but it might tell me that I have some of those present. You know, I don't know which, but I have some present. So what you do is you use this formula. 2 times the number of carbons, so N is the number of carbons, plus 2, minus the number of hydrogens, plus any nitrogens present, minus any halogens present, like chlorine or bromine. And then you divide it by 2. So let's try that out. 2 times the number of carbons is 5 for this molecule, plus 2, minus the number of hydrogens, well, that's 12. I don't have any nitrogens or halogens, so I'm done. So 2 times 5 is 10, plus 2 is 12. 12 minus 12 equals 0. Divided by 2 is 0. 0 degrees. That means that C5H12 is saturated and there are no double bonds or rings in that structure. So you can see how it's starting to tell you something about what might be or might not be present. This will help you when you're given a molecular formula and other instrumentation methods. You can start piecing things together and figuring out what your molecular structure must be. So I'll leave the rest for you guys to try as more practice in determining degrees of unsaturation.